Hello and welcome back to this latest video in the series of videos that we're doing with the repeater digital card and repeater analog card. So we've covered the whole thing really quite detailed so far, and now we want to look at schematic diagram entry into KiCad and leading on to some PCB design, so we can get the whole thing, the old analog card, onto a PCB. Right, so first thing we need to do is open up KiCad. And let's have a look at this. I've already created a new project here called Analog Card, so we're ready to go on there. So let's just open up the schematic designer. Yeah, so here we are. One of the first things I tend to do with KiCad when I get started is increase the size of the form that we have to enter the schematic diagram. So this is an A4 size by default, and I find it's better to go up to an A3 size. If you double click on here, it brings up this dialog here. So there you are. At the moment it's an A4 size, and personally I tend to go for an A3, which gives us a better working area, so you can get more components on the sheet. Issue date, we'll just make that today, and revision, let's say it's 1.0 for now, and this is going to be the 6502 analog card. Okay, so that's what this is. Company, well, it's not a company, so I'll just put my call sign in there for now. And yeah, so let's go with that, and you'll notice straight away that the everything's been updated. Here's the legend at the bottom, and we've got the title in, we've got the date, and it's revision 1.0 for now. I'm zooming in and out very easily just using the mouse wheel, the little scroll wheel on the mouse, and you just hover over the area you want to go to, and you can just like zoom in very quickly. I find that very efficient. Probably start by saving what we have, and the next step now will be to take some of the components and the schematic diagrams that we have on bits of paper that we've drawn down during the development process and the prototyping process, and enter those pieces of circuit into KiCad. And I'll just go ahead and make a start on that now. So the first thing I'm going to do is to place a 4066, so we'll go up here to add symbol. And of course it's going to have to load in all of my libraries, so let's just wait a moment. Yeah, this took quite a long time on my computer because it's not particularly fast with all of the available libraries. Let's try 4066. There we go, there's some symbols for a 4066 up here. But basically it's a switch with a control line in the middle there. And we've got 4 of these per package, so we shall say I think we actually have variants. You've got A, B, C and D, but that seems to be quite alright, so we'll just select that, and let's just start by putting on. Now of course what you can do is you can rotate these pressing R on the keyboard, so you can have it that way, that way, that way, or that way. I'm gonna not really sure which way to go. I'm just going to do them this way. So this is package A. I think I'll do them vertically like that, but it may change. So there's one. Okay, let's do another one. This is going to give us package B, like that. And over here, let's try package C. Or unit, really, it's not package, is it? It's unit C and unit D within one package. C and D. So right hand click to get rid of that, press escape, there we go. So there's our 4 bilateral switches as part of the single package of a 4066, and that's going to be our central switching for all of the audio to come through. I'm just going to go ahead and add some extra components, and we'll cut the video and I'll come straight back. Okay, I've added a few components, and just to, show some of the process, that's all, without doing the whole thing. So here we have a trimmer, a variable trimmer, and this is going to be the CW mute control, which will set the difference between loud CW ident and quiet CW ident. Now this connects between the unit A, unit B, so all we need to do is connect these up with a bit of wire, so we can click in there, put a bit of wire in there. You can see it sort of goes green. Okay, and also on the other side as well, and the center terminal, or the wiper, basically shorts out to one end of the trimmer. So that's connecting, if you like, the in-out of one of the switches to the in-out of the other switch, and that's basically going to be the CW level, whether it's loud or quiet. This 100N here also connects to that point, so I'll just go ahead and connect that up. Okay, and all I'm doing is just clicking with the left hand button on the mouse and putting in connections. I'm also using the mouse wheel, as I mentioned earlier, just to get around the diagram very quickly. It's very, very rapid. You just move to where you want to go and zoom in. There's a capacitor, and so on. Other side of this capacitor goes to a 1K. I'll just add that now. Add a symbol. And you'll notice I've already got some parts going on here, so I'll just use that again. Use R4 resistor, and we'll put that in here somewhere. I'm not quite sure where. I'll just put it here. Press escape, and then you can join them up with a bit of wire. There you go. And I may have to change this. I think that's a simulation capacitor that I've used. It doesn't quite look right. We'll try and add a different type of capacitor. Just type cap, and really we'll want something, yeah, I've got the wrong one. This is all P-Spice, isn't it? Yeah. There you go, down here. We want a non-polarized in this particular instance. There's probably other one. Polarized is for electrolytics. Well, we're not using those yet. So for this, it's just, I guess it's just a standard small. Oh, there's the one there. That's better. Unpolarized, that's what we want. So, because you can put it in any which way around you like. So let's use that. And what I'm going to do is I'm just going to put this here. You press R to rotate it. Use the R key. I'm just going to put that there and remove this. Drag this into here instead. Now we've got the proper symbol. Yeah, because I mean there's P-Spice symbols in here as well, so you can do circuit simulation and whatnot, but we're not doing that in this particular case. Okay, so there's a capacitor there. The value of that capacitor is 100 NF, so I'll click on where it says C and type in 100 N. That's now 100 NF capacitor there. Right, so what was I doing? So down here we've got a fixed resistor of 1K, so again click that, type in 1K. There's over 1K. These values may have changed while I was experimenting with the prototype, so I'm putting these in now, but they may change once I've had a closer look at the board. I think I made a few changes and didn't write it on my sheets, which I should have done. But so what I'll do is I'll, you know, before we commit this to PCB or anything like that, long before we get to that point, we'll just quickly go over the prototype boards that we've made, and we shall check that the component values are indeed what we're supposed to have, what we ended up with. So we need to put in a trimming resistor. Now another way you can do this is just select a part like this trimmer here and do, you know, the standard copy and paste, Control C, Control V, and you can drop that right in here. I need to rotate it so it's pointing that way, and I'll put this down here somewhere. There you go, and join it up so that that 1K goes into here, into the center wiper, and the value of this is a 10K preset. Again, these values may change. The bottom of the resistor goes to ground, so let's place in our 0 volts, I suppose. Let's have a look. Add power, And these are all the power options here. Well, we just want a 0 really, or a ground. GND would do it. That'll do it. So let's select this here. GND. There's, you know, you could have NOD volts. There's audio grounds. There's digital grounds. Really depends on the project that you're working on. Should be a 0 up here somewhere, I would have thought. Well, there's a, yeah, I guess you could make your own, but there you go. We'll just use ground. Okay, and that basically goes to ground there. So the bottom of this trimmer is going to connect to ground, and that's it. So now this trimmer, which is actually the CW level, like the overall CW level, is for that. Now the top of this then goes to another part of the circuit. I think I'm going to actually have to drag this down a bit. You can select the area and drag, which is fantastic. And then you just place that where you want it. I'll put that there for now. You'll notice I've got a 10K up here. Hope you can see this okay. There's a 10K up here. Let's see what that's all about. Now that connects to the control lines of unit B and C. Let's have a look. Control line. Sorry, B and D, I beg your pardon. So these two. These are the control lines, so we need to connect these together, kind of like that, and then like that there. So that's joined up the control line of this bilateral switch to the control line of this bilateral switch on the 4066. Doesn't really matter if it's A, B, C, D, as long as you know, you actually, the positions of these don't really matter. When you come to do the PCB, things will just get routed anyway. You may want to change it later for, you know, to make the PCB a little bit more efficient. See how it goes. Okay, I've got a rough idea how it should lay out, but it may change. That's normal when you come to designing or entering in schematics or PCBs. You know, you do find that things get moved around constantly when you make better decisions. Okay, so those two control lines are now connected together. This is basically a pull down resistor to ground. That's what this is doing. So we need to connect that top part to the control line, and the bottom of the resistor will be another ground. I'm going to do what we did earlier. I'm just going to copy with Control C and Control V and stick it right over there. That basically just saves us having to, you know, go up here to the place and the power and select the ground. You don't have to keep doing that all the time. Once you've started and you've got a few components on the circuit, I tend to just copy and paste them in and change the values as you go. You could also drag numbers around, the values and the annotated part number. Once it gets annotated, you can drag those around as well, just for neatness. I tend to pull them in a little bit, but that's all stuff you can do at the end when you've finished your layout. Okay, so here you are, we've made a start. I'm going to press save. There you are, it's saved. Good idea to save every so often. And I'll just keep going, and all I'm doing is looking at my sheets in front of me here, penciled in pieces of circuit, and I'm just one component at a time entering them in and connecting them up, you know, with these wire links and what have you, and we'll just keep going. So I'm going to do a bit of a jump cut and enter more schematic in, and we'll come straight back. Alright, so I've gone ahead and added some more components, as you can see, to the schematic. I've also made a few changes. I reversed positions of Unit D and Unit C. I'll explain that later. Basically, it's just I know the PCB layout was going to be easier. I can see it coming. And I've added in this bit of circuit down here, which is basically the audio mixer, if you like. So, and I've added some labels like CW level, how loud the CW ID is, and audio level, that's the actual rebroadcast speech level. And it's just a very simple passive mixer. These controls will interact with each other, but you know, that's kind of how it is with this particular design. We're not trying to go too far with active mixing or addition of summation of audio levels or anything. You could go further, but there really isn't any need for what we're doing here. And I've added a little label up here for the CW mute level, which reduces the level of the CW ident. Doesn't turn it off, it just makes it quieter. So yeah, move things around a bit. You'll notice I've got some labels, like here I've got CW OSC and CW in. So the CW oscillator, which is the sine wave audio oscillator, will come in here and through this switch here. This CW in label here is a TTL 5 volt level with a pull down resistor, and it's going to be connected directly to the 6502 card from the digital side. And what we're doing with these labels being positioned like this, and not having wires coming all the way from here to a big connector at the other end of the board or something, is just to reduce the visible amount of wiring that we have. It's the same sort of idea that we have with grounds being everywhere. If you didn't have these common points or common labels which will be connected elsewhere, you would have wires running all over the place. All of the grounds would have to be physically all wired. This CW OSC signal would have to connect to the CW oscillator, which is coming later. This CW in would have to go all the way over to the, the edge connector or the DIL header on the end of the board. So it really just reduces the amount of wire that we see in the diagram. And as long as you understand that whenever you see a label like this with something written in it, it will connect to the same label elsewhere, somewhere else in the schematic. And you've just got to do that in your head, connect those two labels together. As long as they're identical, they will connect. They're on the same node, if you like. So there we are, made a good start. That is more or less the switching circuit. Again, this might all change once I've had a look at the actual board, but this is just the rough notes that I've got written down in front of me here. Let's save that. Now, one thing I haven't got on here is any power to the 4066 package. So let's do that right now. And one way you can do this, there's different ways you can do it, but you can add another part within the package. Now you'll notice we've got A, B, C and D already used here. There's also a part E, E for echo, and it is, in this particular case, the power pins. So if I copy this part, Control C, Control V, and stick it here, so we're just making a copy, okay? Seems a bit pointless. So what you can do is right and click that and go to Properties here, and you can select which part you want here. See, it says Unit, so we're on Unit D. This needs to change to Unit E, okay? Unit E, and then select OK. Now you'll see that it looks completely different. And if we highlight that and rotate it, we now have power for the 4066 power pins. Anyway, it's pins 7 and 14, standard power pins for a 14-pin package. So we can take our ground, Control C, Control V again, and connect that to ground. There you go. So that's now got a ground pin. Mush that in a little bit. And for the top, we need our 5 volt rail, so we're going to have to place, we haven't got one yet, so we're going to have to start with our power, add power here, and look for +5. Don't forget our system's now working on a +5 rail, a standard +5 rail, so it's easy to get the voltages right. We've got no complications with different voltages or anything anymore, or negative voltages for that matter. It's all running from a +5 rail, so that's our +5 symbol. And that's going to be our power rail. So let's put him up here. Okay, just like that. And connect it up again. Simple as that. And we can drag that down just for neatness, I suppose. There you go. We can put a decoupling capacitor on here to ground if we wish. We've already got decoupling capacitors elsewhere on the board. And to be honest, this has not been clocked at any particularly high frequency at all. It's just CW, which is really slow clocking rate. However, you do actually have fast rise and fall transitions on that, so you could actually put a decoupling capacitor on there if you wish. I'll leave it off for now, but you never know, we might add one later. So let's just click save there, and that's the power. Now normally what you do is when you end up with situations like this, you would take this part In fact, you'd highlight the whole area, highlight that all with the positive +5 in the ground, and drag the whole thing out of the way. Okay, just, you might end up with it down here or up here, and as the design develops, you'll notice for the different chips you end up with a bunch of power rails for all the different chips. They'll appear in a block. Normally put them all together, and again, that's just to get rid of complexity from the part of the circuit that you're actually interested in, the bit that does the job, the business end, if you if you like, but and get all of the power out of the way. But they do need to be connected for when you come to do your design rules. Everything has to be connected. It will check that if the power pins are connected or not. If they're not connected, it'll give you an error. So they do need to be connected. And any other chips that you add or any other rails, they will all connect up here. You can put them anywhere you want, you just drag them around. Let's just say the power is taken care of because of that symbol up there. There is another thing that you need to do as well, just thinking about this while we're talking about power, and it's a bit of a thing that you have to do with KiCad, is you actually have to designate that these really are connected to power, not just like free labels, if you like. So you need to place, let's have a look here, add power again, but this time we are adding, let's have a look, power flag. You see that's a power flag? So this tells KiCad that that really is going to be connected to a power rail. Again, when you come to do the design rail checking, it instructs KiCad that yes, it is actually going to be connected to a power rail, not just floating with a +5 tag on it there. So your power flag needs to be connected there. Now you just simply connect it to your power rail. You only have to do this once somewhere in the diagram, doesn't matter where you do it. And I'm going to copy that to the ground as well. I'm going to flip the top and bottom positions with this symbol up here, like that. So it means I can drag it out the way a little bit and shift it to that side. All I'm doing is just sort of like mushing things in a bit, getting things a bit closer. Zoom in with the scroll wheel. Oops, what am I doing? Yeah, and connect that to there. Okay, so we've got our two power flags. This instructs KiCad, as I said earlier, that these labels here, +5 and ground, really are connected to some sort of power rail in the final design, and it's not just tags that are not connected anywhere else in the circuit. Right, so that's something you've got to remember to do on all of your designs, really. Save that, so that's all the power taken care of. Again, you could add in decoupling capacitors if you wish. I'm not going to do that right now. I don't even think I need them. So next, we'll look at expanding this. We've got the CW oscillator section to build. We've got the CTCSS decoder section to add, which is going to be an Atmel 328P. Another thing you can do is add sheets, different sheets, and you can add other sheets. Let's have a look now. Yeah, this is the root sheet. That's where we are now. And it's really handy for separating out complex diagrams. You know, I may actually do another sheet for the CTCSS decoder, possibly, unless it fits down here. If I can get the whole thing on one sheet, I will put it on one sheet. But with complex designs, you know, you have a lot of circuit, and you may want to create a new sheet with this hierarchical system. Let's just have a look. So you go to place and you can add a sheet. See that there? Or you can just press S by the looks of it. Add sheet. You can draw the sheet up here just like that. Click and then click again. Give it a sheet name. This could be CTCSS. Okay, for the next section. Yeah, like that. So this is like the root sheet, if you like, the one we're working at now. If we wanted to put the CTCSS circuitry on a separate sheet, just for convenience, keeps things separated, keeps the diagram uncluttered, we can double click on there, and now we've got a new sheet. You see this? And it's named it as CTCSS, which is great. It doesn't have any revision information, but you can copy it all if you wish from the root sheet. And in here, place our components and build up, the whole CTCSS circuitry around the Atmel 328P and some other parts, crystal, whatnot. And that could all go on this sheet. So I'm just going to leave this sheet blank and go back to the root. And you do that here, or you can use the little arrow here, which takes us back to the root sheet. And you can have multiple sheets. You can make multiple sheets here just by using place and add sheet. Okay, so I shall click save, and there you go. So yeah, audio switching entered. I do need to check the values, and we'll keep going. So another jump cut. Let's see how far we get for the next section. Okay, and now we're back. So as you can see, I've gone ahead and added some more to the schematic diagram. This is the section where we're just looking at audio mixing and switching, and we've added this section here, which is the CW oscillator. It's a pretty standard circuit. It's a phase shift oscillator, and you can see the components that if you like set up the phase shifting, and the frequency of the oscillator is just here, and the output of this, which is actually this point just here. It's not the output of the op amp like you might think it is. That would give probably a square wave output. It's here, which gives us a sine wave. This sine wave is 150 millivolts, peak to peak, that is, and this is then amplified with a ×10 buffer. So 150 millivolts in, and you get approximately 1.5 volts peak to peak out, which is more than enough for our audio signal. If anything, we might even reduce this a bit if it seems to be too loud or too much to adjust to bring back down. Probably don't need that sort of level of signal, but we'll see how it goes. So that's our sine wave oscillator. You'll notice that the output of this has this label CW OSC, which basically connects directly to this label here. See, those have got the same label. You could just imagine a piece of wire between them. And basically all we're doing is we're taking this oscillator sine wave, putting it in here, and turning the sine wave on and off. That's our CW ident, and the rest of it, well, we've already explained. So that's the CW oscillator with a little buffer on the output. I've also gone ahead and added this section here. This is the CTCSS low pass filter. The discriminator from the RX radio, from the receiving radio, comes in here, goes through this low pass filter arrangement using this LM324 is the active component. The output of the low pass filter, which it says up here, it's roughly about everything below 228 Hertz, which is exactly the sort of region that we want for CTCSS. Anything above that is cut off, i.e. the speech is reduced and cut off. That then goes to this section here, which I've just called digitizer. Basically it makes square waves out of the output of this, so it's going through sort of a chopper, if you like, or a digitizer, and that gives us a logic output digi CTCSS. This will connect to the CTCSS detector circuit, which I haven't added just yet. That'll be an input pin, actually an interrupt input pin on the Atmel 328P when we get that far. That's given us a 0 to 5 volt TTL output, if you like, representation of the signal coming in. So that's all part of the CTCSS input circuit, low pass filter and digitizer, and we've added the CW oscillator. Now you'll notice that there are, I'll zoom in a bit, there are 4 units, 1, 2, 3 and 4, and just out of sheer luck, it means that we can get all of this circuitry into one chip. I was thinking we might have had to use a couple of LM324s, but it looks as if we can kind of squeeze it into one. Okay, now last thing I want to show you is what we've done with the power supply rails here. Now there's the 4066 that we talked about earlier, and we've got our power flags in to keep KiCad happy that it is actually connected to power. We've got a plus 5 volt rail and a ground. You'll notice we've got a few components here, and we've created a V-mid and that just means voltage in the middle. So +5 on the top, 0 on the bottom. This will give us 2.5 volts DC, V mid rail, and we use this for driving op amps to keep them central, keep them away from the +5 or the 0 rail, keeps them V mid, and we use that for various op amps later on. So we've got a couple of resistors, just a resistor divider there, a couple of capacitors across there to reduce noise and decouple them a little bit in case to stop interference from one section to another. And also you'll notice we've got this looks a little bit strange. This is the power supply pins for the LM324 and for the circuits we've just been looking at. It doesn't have this box like this one does. It's a bit of a shame. Sometimes this happens. You know, the actual circuit symbol can be slightly different, but it does exactly the same job. It just looks a bit different, but you know, pretty much that is exactly the same as this. We've got the V plus, which is pin 4 in this case, going to the positive rail, and we have V minus, which is going to the ground rail. So that's pin 11 for minus, pin 4 for positive. That means the power supply to the LM324 is connected. Right, and we've got a little decoupling capacitor on the right across the actual rail there. Power supply with V mid, and as I say, that's pretty much as far as we've got. I think that's generally all of the audio side taken care of. We're now going to look at the CTCSS decoder with the microcontroller Atmel 328, and as we discussed earlier, I think it's fair to say I can easily get it on here. I've got loads of room here. I don't think there's any need to use the separate sheet that we made earlier, but that was just worth pointing out. Sometimes you really do need multiple sheets. When the circuits start to get much more complicated than this, you end up with you know, you end up with a lot of components, and you just want to separate things out and make it more logical when you want to inspect the circuit later or make a modification. This makes it much easier. And there's our V mid in use there from the power supply, and that's just basically going to the positive input of that LM324 to keep it at mid rail. It's also another V mid down here as well, doing the same with the oscillator op amp. I believe it's used somewhere else as well, but yeah, that's basically it. Okay, so onward. We're making good progress here. Let's get the CTCSS microcontroller into the circuit. Let's do that now. So the first thing we want to do is place the microcontroller on the sheet. So let's add a symbol like we've done many times before. Select add symbol. Go to the library, the symbol library, and we can type in, I think a part of the number would work. If I say 328P, does it know what I'm talking about? Yes, it does. And here they are here. There are different versions. That's a DIP 28, dual inline package 28. If we weren't going to use any surface mount parts, that would be the choice that we would want. That's a standard plug-in device. But we're going to be using surface mount, one of these, I think. Probably, I'm just going to flick through and see what takes my fancy here. Yeah, it's not a, we don't want a QFN. It's going to be a TQFP package, probably, let's say, want either that one or that one. These look pretty much the same. Right, so I think we're going to select the 328, it's called a PB-A, and basically it is the TQFP32 package. So let's have that. Right, so, and then you can look at the you know, the general layout of the sheet, and it's probably going to be reasonable to put it over here since we have a bit of a gap. Don't forget you can always move things around, so I'll select that. We'll just put that there for now, and don't forget you can, you know, you could grab all of that part of the circuit and you can put it anywhere you like. You can move the whole thing if you wanted to. I'll put it up there a little bit. There you go. So now we've got like loads of space down here for our 328 PBA. Now we could actually use a DIP 28 package and even put it on a holder. I mean, if you wanted to do that, we could do that, and then you could pull the chip out, program it, push it back in again. But what I'm going to do is I'm going to actually solder the chip to the board as a surface mount device, so it's non-removable, and have a small 6-pin DIL header, which you can then plug a programmer into, like the Atmel programmer, which allows you to program the device on the board in situ. So I find that actually a good way of doing it. The only thing is that you do end up with a little 6-pin DIL header, which doesn't really do anything except when you come to program the chip. The way I look at it is why not just put the pins on the board, and then you can program it directly on the board without having to remove the chip and put it into a separate programmer or something. So that's kind of how I like doing it. But you know, you could actually use a 28-pin dual in 9 package and just put it on a holder and pull the whole chip out to program it. So yeah, right, so there's our chip, and what I'm going to do now is we'll do another jump cut and we'll get this thing wired up. So here we go to the next section, and I've added a couple of things here, but the main thing of interest is the CTCSS decoder, which is based around the Atmel AT-MEGA328P-A. You'll notice that numbers changed slightly. I had picked the wrong chip and I realised afterwards it would have worked, the one that we did have. I think it was a BP-A. This is just the P-A. Whereas it doesn't have, I think the PB-A, if I'm getting that correct, has extra ports. I think it's got PE0 to PE3. It's got an extra 4 inputs or something like that, and we don't need them. So I've changed it to this one, which is the standard 328P-A. Okay, so and we've connected it up, as you can see, little 5-volt rail decoupling capacitor on the power there. A lot of these pins are not used. PB0 to PB2 is not used. You notice we've got these X's here. You've got to select pins that are not being used as no connect flag. So it says add no connect flag there. Click these on all of the unused pins. Again, so when you're on the rule checks in the ERC and in KiCad, it knows that these pins are meant to be disconnected, and there's a few more down the bottom here as well. So I've already done those, as you can see. So that's a no connect flag on any pins of any devices that are not being used. You must actually show them as no connects, otherwise you'll get an error. I've got a little bit of text going on down here. The signal in is on PD2, which is int 0. PD2 is this one here. It's our pin 32 in our case. Detect out is on PB5, SCK. Well, PB5 is here. PB5, pin 17. Let's have a look. And this is the output, and what we've got is a CTCSS detect label. I'll show you where that goes in a second. And also we've got an LED, which I've just realised is round the wrong way. Ha! Gotcha. Let's fix that right now. Put that there, and we need to rotate it. Press R. There you go. And I'm going to shift the legend over to the other side. That's a little bit messy there, isn't it? It's not very good. Yeah, I think I need to flip the whole thing. You can flip with these controls up here, either vertically or horizontally. Well, I need to do a horizontal flip. Yeah, that's better. Now I can move the legend out the way over that side. Just drag things around as you need them. Yeah, because the CTCSS detect line is active low. So when that line goes low, we want the LED to come on. So yeah, I had it around the wrong way. I've just realised that. There you are, quick fix. We'll save that now. Now this CTCSS detect label, you'll notice it goes up here where we've added a connector, and I'll come to that in a second. There's the CTCSS detect level, and it goes to pin 6 on our connector that I've designated for the card. So this is all of the signals coming in and out of the card, going to various labels within the circuit. And that's the one we've just looked at there, which is CTCSS detect. So when we get a CTCSS tone, this logic level will go low, which is pin 6 on our header. You notice we've got a dip switch in here. It's a 6-position dip switch, DIP switch. Connects to PC0 to PC5. That gives us 6 switches. And these select which channel we want to detect. It's a hardware solution. There's different ways of doing this. We could have done a software solution where you program the chip, which, then you could actually sort of remotely change it. And we could do that later. But for now, just to keep things simple, I thought, no, we'll just put on a very simple dip switch. And you use a fine point prodder or a screwdriver, and you just flick the switches to the channel selection that you want. They all go to ground, and basically these are actually pulled up high internally through the firmware. We've got a 16 megahertz crystal here. If you remember when we did the prototype testing, there is a way to get this chip to work without any external oscillator, without any external crystal, using the internal 8 megahertz oscillator, and it works, it does work, but it wasn't quite as good, it wasn't quite as selective as using the external 16 megahertz oscillator crystal. So I've left it in, and we're going to put that in the board. What else can we talk about? This is the reset line here. PC6 is the reset, which resets the chip on power on. We'll have a little CR circuit here, which basically gives us a low reset signal on power on. When it settles, it goes to high. Now, what I haven't showed you yet here is this, and this is just a 6-pin header, 3 either side. It's a dual inline header, and what this is for, as I mentioned earlier, is for ISP programming. Now, this connects to various pins to the Atmel, and they just work out as being these pins here. If you look at the data sheets, this is all catalogued. You can figure out why I've connected these pins here to these pins here. There is a standard way of doing that, and basically this is going to be our connector for the programmer. So it means we can actually send our firmware updates and changes and anything we like into the chip, program the chip without removing the chip from the board, which is I think that's actually quite handy. So that's the in-circuit programmer connection. Now I've added this. Now this isn't in the prototype. Inside of the Atmel, you do have TX and RX serial comms lines. You can actually transmit serially and receive serially to the chip. It's quite handy. Could come in handy for diagnostics. Could come in handy for external channel programming if we wish. It could be, I don't know, anything you can think of really. Test modes, So what I thought was, let's put a little connector on here. Pin 2 is the receive line, pin 1 is the transmit line, and these go through just a couple of 100 ohm resistors just for protection, in case you short these out or anything. Gives the chip a little bit of protection. And basically these go into the chip so we can run serial comms, possibly RS-232, anything like that. So it gives us a chance to have a bit play later down the road when we've actually completed the circuit, and we can maybe have some text coming out of there serially, some diagnostics, anything we like, and have a bit play with that. So it's just for the sake of like 3 components, it's worth putting it on so we can actually play with the serial functions later. Yeah, so that's basically the whole decoder. So we've got digital CTCSS signals coming in, and we've got CTCSS detection logic level out. That's kind of it. So if you look at this whole thing, and you might think, oh, it looks a bit complicated. It's basically 1 input pin and 1 output pin. So with some programming switches to select which channel you want. So it's actually quite simple. We've looked at the connector, which connects to various parts. We've got discriminator input. That's going to be our sub audio in from the receiver. Audio input, which is speech, if you like. Audio output goes to the transmitter. We'll have a CTCSS detect logic level that goes to the controller card. PTT is the actual pin that goes to the transmitter to activate the transmitter to make it go into transmit. Mute in is the signal from the 6502 controller card to make the CWI go quiet. CW in is what it says on the tin. It's CW coming in, and TX is our, if you like, it controls the PTT line. So the TX goes to the 6502 controller and it turns the PTT line on and off. So if you like, the signal's coming through TX and it's coming back out through PTT to the radio. And that is the whole connector there. You'll notice I've got a few ground connections. So pin 12 and pin 11 will be a pair, possibly coax. Pin 10 and pin 9 will probably be another little coax for the audio there. 8 and 7 will be another little coax, and that's the audio out, and so on. These are logic lines, so they don't matter. And they don't need extra grounds, but there is a ground on the bottom anyway. Right, that's going to be the connector. You'll notice on the power supply I've added a 500 milliamp fuse just for safety, and we've also got another little connector which is going to be our 5-volt input power coming from a regulated supply, probably a little switch mode power supply or something. Put that in a box. That's going to drive this directly. This is the PTT switching circuit, so there's our logic level coming in here from the 6502 card. Very simple, little switch transistor, switching transistor, little diode there for protection, make sure nothing goes the opposite direction, stops back EMF from anything from coils or anything like that. So that gives us, protects the transistor up to a point. That's the PTT line which goes to the connector, which goes to the transmitter PTT line. And I think that's kind of it. Did I miss anything? So yeah, I may change these labels. I'm thinking about disk in. Well, it depends which way you look at it. I mean, this is an input, but it's not a discriminator input. If you like, it's discriminator output, or low. It really should be low pass filter input, but then you don't know what it's for. So coming up with labels that actually make sense, yeah, that can get a bit funny sometimes. We've got a spare 4066 up here which isn't doing anything. If we can think of a use for it, that might come in handy for some purpose later on, but for now it's just disabled. I think that's pretty much it. What I'm going to do now is I'm going to run the ERC, the electrical rule check, and I'm pretty sure we're going to get errors because I've just flew through this rather quickly. So I'm going to do inspect, and it's up here, electrical rules checker, ERC. Okay, first thing it's telling us is the schematic is not annotated. Yeah, of course it's not, because I haven't done it yet. What you'll notice is that we've got R question mark, U question mark, A, RV question mark. They don't actually have any designated part numbers, if you like. So what we need to do first is go to Tools, and annotate the schematic, which is here from the Tools tab. Annotate schematic, and I'm just going to say annotate and just do it basically. Now you'll notice that it's changed, and we've got RV2 here, we've got U2D, all the question marks have gone, R14 for that resistor here, you know, so it's been annotated. I'll just save that now, and let's try running the inspector again, the electrical rules checker, and run ERC. I know there's something going to be wrong, there always is. Right, so what it says is we've got a problem with global label CTCSS disk. Yeah, so actually we've done pretty good. Look, there's no errors. We've only got a warning. So what's in messages? Yeah, that's fine. So we've only got one warning. I'm quite surprised. It's the first time I've actually run this. Let's have a look anyway. So yeah, and sure enough, you'll notice it puts like a orange coloured, yellow coloured, I don't know, orange coloured arrow there, and it's telling us that this label is an error. And the reason why it's an error is because it doesn't connect to anything. That's true, it doesn't actually connect to anything. I think what I'm going to do is I'm just going to remove that for now. That's why it says optional, and I'm going to put a no connect flag on that point just for now. Add no connect flag, and we're just going to zap that with a no connect. There you go. We'll save that. It means that there'll be a couple of components on the board, or at least positions for them, and I don't know what to do with the end. Maybe we'll just put it to a pin or something, or a pad on the board. that we can solder to maybe. Okay, let's run the inspection again and run ERC. And what do you know, we are error free. Now the sort of problems that you would get are things like if you'd forgot to put in the power flags. That's a really common one. Got to get them power flags in. Things like that. All of the labels must connect somewhere. They've got to match with something else on the board. So, you know, you can't, like what we just did with this optional one that I've just removed now. Things like that. It wasn't connected to anything, and the electrical rule checker picked that up and says, hang on, you've got a problem there. So all I've done there is just made it disconnected. And then it says, okay, it understands that we just don't want to connect it to anything just yet. So yes, we are actually at a point. Electrical rules checker, run ERC. I'm just checking it again. And yeah, well, would you believe it? We've got no errors. So it thinks everything's all right. Other things that it tends to pick up on is if you haven't, you know, no connect flags on disused pins. Let's give that a go. Just as a test, I'm going to remove one. Okay, there, I've removed one from pin 11 there of this chip. Let's run the inspection again. Electrical rules checker. Should pick that up. Run ERC. There it is. It actually tells us symbol U3. Sorry, this is a bit small. Symbol U3 of the 80 mega. Pin 11. PD7. It even knows which pin it is. Okay, there's a problem. It says not connected. Not connected. And there's a big red arrow there saying you need to do something. Right, all I'm going to do is just undo that delete that I did there and put it back. There you go. Save that. Let's run the inspection again. And run. And now you'll see we've got green here. No errors and no warnings. Fabulous. Now, pretty much this is our circuit for the analog card. Pretty much complete. I bet there's going to be some kind of change somewhere along the line, but for now let's just assume we've got what we wanted. I think we're going to wind up the video at this point. It's already getting a bit long. I think the next section will be to open up the PCB designer and load the components onto the board. We're going to have to fill in things like footprint symbols, because a lot of the components won't have the footprints designated yet, but at least we've got a schematic already. So yeah, that's going to be in the next video. We'll be looking at the PCB. We'll do some, we'll have a look at a 3D view of the board and see what it's going to look like once we've actually got things located in the positions where we want them. We'll leave it there. Comment below if you like this kind of thing. If you don't like this kind of thing, comment anywhere. It's all good. If you like what you've seen so far with this schematic designer, give us a like and don't forget to subscribe. So thanks very much for watching. See you next time.